Okay, have you done registration? I will give later after one class hour. I will give you a chance. Okay, let me start because time is very strange today. Something wrong. Chapter 1, we have to finish chapter 1. So can you see my screen?
Yes, sir.
Can I? And are you hearing me well?
Yes,
Yes, can hear.
Okay. Because your voice is also very low. Okay. Okay. First of all, let me stop sharing and record first. Okay, let me recording. Okay, now recording is on. Sharing screen. This one I will make small. Put it here. Okay. So now, before starting, actually, I want to tell you, I prepared the quiz for tomorrow, but only tomorrow evening. Hey, actually, Ramadan started. Now, 9 o'clock, usually we cannot finish our Tarawih. So what time is convenient for you? 10 o'clock is okay?
Sorry, doctor.
Huh?
What you say?
I
Cannot hear
mean,
well.
tomorrow we have the quiz 1.
Okay.
So there are two choices actually. One is I will finish my class just after half hours. I will finish, and you can continue the quiz. This is one choice. The second one, I complete the full hours. Then tomorrow evening, for example, 10 o'clock, you will sit for the exam. Which one is better?
First choice, maybe.
Huh?
First choice.
First choice. So
First
for me,
choice.
as male Muslim, pray Tarawih, maybe 10:30 done.
10:30. Yeah, after Tarawih, actually around 10, minimum 10, otherwise 10:30. If 10:30 too late and you are very tired, how?
Maybe first choice, doctor. Can?
I think first choice we do, because actually the two questions only. One questions I choose from these lecture notes for the proof by using the axioms. This second one, I choose the second my lecture notes, the Matrova lecture notes. So generally, the one is I can say it is already stated there. The one is the principle of mathematical induction, and the first one is based on the axioms, proof. Both of them proof. Very simple. Actually, it is not the difficult questions, but still you need the practice. Okay, so please practice all the examples. I mean the exercise in this lecture notes. This lecture notes number 1, and second one, you please look at Matrova, the second one, and mostly you focus on the induction method. Okay, so one question I choose from there, one question from here. So if you revise, I hope no problem at all to get the good marks. And it is actually just 15-20 minutes is enough. But I will stop around tomorrow 12:30. I will stop. I will give half hours for sitting exam, another 15 minutes for submission. So total 45 minutes. Okay, after what, so we can finish before the Salat Zuhur. Is it okay?
Yes, for me, okay. Can Tarawih.
Sorry, doctor. Can
I think
uh,
it is okay, everybody. Comfortable?
Yes, comfortable.
Okay, good. I think that way because evening is very tiring, and they cannot maybe focus well during the class. Of course, you will definitely focus. Okay, so in the case today, I will set the exam in the Pembelajaran. You will submit after finishing your class. I will submit MS Word file in order to open easily, to paste easily. Maybe if you are able to write in MS Word directly, you can write. So quite comfortable. I am preparing. Okay, now let me start our class. So Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning. So today, actually, our class is Completeness Axiom. Okay, I'll try to finish this one as much as I can because we are too late. The second chapter needs to start. So generally, what does it mean, completeness exam? So completeness exam starting from the boundedness of the set. Okay, first the definition. Just look at the definition. I think then for the solving the problem, I will use my the whiteboard. So let's say A B the B is the non-empty subset of R. Okay, definition says if there is capital M from R such that all values of X from A is less than or equal to M. So in other words, if any element of A satisfies this inequality, then M is called upper bound of A. And the set A is said to be bounded above. You see, first, two things. The capital M is the upper bound of A, and set A is said to be bounded above. Similarly, if there is small m from R such that all values of X from A is greater or equal to M, then M is called lower bound of A, and A is said bounded below. The third definition says if A is bounded, then it is bounded if it is bounded above and bounded below, and unbounded if it is not bounded. You see, this unbounded actually, if one part, for example, upper bound doesn't exist, it is called unbounded. If all lower bound doesn't exist, also it is called unbounded. For example, here there is this example, for example, this example is unbounded. Even the one side is bounded, second side is unbounded. It is called unbounded set. Okay. And here, good example. You see, this A is bounded above by 1, and it is bounded below by 0. So actually, this set is bounded set. But even it is, you see, half open set. So this set is called bounded set. And here, another issue. Please pay attention. The second definition. So please pay attention here. Just this example shows that set A is bounded. Okay, now very important and very sensitive definition 2. Please pay attention. Let A be the subset of R, and element B is called a least upper bound. You see, least upper bound or supremum of A, denoted by supremum A. If B is an upper bound of A. Okay. This is B is the upper bound. That is this inequality holds for all X from A. This is the upper bound definition. But second one, there is no upper bound of A which is less than B. In other words, this is the important inequality. You satisfy this equation for all X from A. You see, similar definition as B. You see, B is greater or equal to X for all X belong A. So here U is also same. If there is no upper bound of less than B. So if any U is satisfying the same inequality, then it is implies U is greater or equal to B. So in other words, if we subtract epsilon, very small epsilon number from B, then the B minus epsilon is less than X. There is a X less than B minus epsilon. Okay, so it means the supremum is the element such that we cannot deduct any number from upper bound. If very small, very small number we subtract, there is X from A such that this inequality doesn't hold. Okay, so that is the this upper bound definition. So please pay attention. This is a main important. If U is another upper bound, you see, upper bound, then U should be greater than B. Similarly, we call A is the greatest lower bound or infimum, denoted by if A is the lower bound of A, which means satisfies this inequality, and there is no lower bound of A which is greater than A. You see, here less than B, here greater than A. In other words, if U is a lower bound for A, then it implies U is less than or equal to A. Okay, so that the second definition is very important to identify the set has a supremum or infimum, and you will see some examples that the A has a supremum but not maximum, and has infimum but no minimum of the set. Okay, so I will give a few good examples. So it should be noted that if there is a least upper bound of A, it must be unique. This is another, you see, upper bound can be any. So if B is the upper bound for A, for example, for A, any number greater than B is the upper bound. So upper bound has many. We can say infinitely many. Lower bound is also same. Lower bound has many. But supremum or infimum, if there exists, it is only one. For example, here it is said if B and B prime both are the least upper bound of A, then by applying condition 2 with B as a least upper bound, B prime is an upper bound, we obtain B prime B prime is greater or equal to B. By reversing the role of B and B prime, we obtain B equal to B prime. So it means B is greater than B prime. Then we found B prime is greater or equal to B. So if two inequalities hold this, if and only if B equal to B prime. So the supremum is unique. If there is a supremum, it is only unique element. Okay, similarly, greatest lower bound also is unique. Okay, when it is exact supremum and infimum, then we must have supremum of A, maximum of A. Look, when this can happen, you see, if supremum of A belong to A, then supremum of A equal to maximum of A. For example, look here, if we consider this, supremum of A is B, infimum of A is A. What about maximum and minimum for this interval? Do we have maximum and minimum? Don't have. Yes, because the maximum of A or minimum of A must belong to A. Must belong to A. It means, for example, if I take the left boundary or right boundary of the interval, so this element should belong to the A. But here we can see this AB doesn't belong to the A. So that's why infimum, but infimum exists, supremum exists, but maximum minimum doesn't exist. Therefore, please pay attention. Supremum and maximum will be the same if supremum of A belong to the A. So this condition satisfies, then they are same. If this one satisfies minimum of A, if infimum of A belong to the A, then infimum of A equal to minimum of A. Okay. So in the second case, what about infimum and minimum of A? Do they say in the case 2? You see, infimum is A. So, the minimum of A is also A, because you see the A belong to the set. Infimum is belong to the set. The supremum exists, but maximum doesn't exist. Okay, so from this example, you can differentiate what is a supremum, what is the infimum. Okay, now how we prove actually the supremum of A is equal to B, infimum of A equal to A. Now this one. Hello. Are you hearing me?
Yes, doctor.
Yes, doctor.
Okay. Okay, for any case, let me send my very strange, my lecture to the email. For any case, if it stops again, I will use my my desktop computer. Very strange. Okay, one moment. For any case, let me send lecture notes to the desktop computer. I mean the email. I will open there. Wow, very strange. Today is so bad. Okay. Okay, one moment. Let me send. Okay, the 1 moment. Real analysis. Chapter 1, chapter 2. Okay. Okay, I hope now, since you are hearing me, okay, now I can continue. Are you okay?
Okay, Doctor.
Okay, so I am sharing again. Oh, okay. At least I have there. So are you okay? Can you see? So let me whiteboard, because here I need to explain. What's my whiteboard? Yeah, very strange. No whiteboard also not working. Very strange. Yeah. Everything is opposite, huh? I can't on. I cannot run. Very strange. So what about, can I use my, okay, at least I can write here. Yeah, very strange. Okay, anyway, so how to, the last one, if cannot, so something wrong. Okay, now please pay attention, how we prove that this interval has supremum B and infimum A. Okay, now here there is a proof, but we should try to understand the the proof. By definition, okay, here, by definition, if interval is given, then definitely B is greater than A. This one is given. And from here, I can say I can take any X from this A. So capital A is like this, from A. Then X is less than or equal to B for any X from A. So means B is the upper bound. It is correct. By definition. So AB is B greater than, and B is the upper bound of A. Now, if U is also upper bound of A, such that U is less than B, you see, U is also upper bound. If it is upper bound, so it means that it satisfies this inequality for every X from A. So this one is also upper bound. You see here, X, if U is the upper bound of A such that U less than B, okay, less than B. Under this condition, this is we are saying that u is also upper bound, but satisfying this inequality. Then what happened? Now look. Of course, if u is the upper bound, it should be greater than a. But why it is less than this? This one I will explain. A is less than u, and u is u over 2 plus u over 2. Okay? Now, if u is less than b, then it is less than u over 2 plus b over 2, which is u plus b over 2. Okay? So, you see, u satisfies this inequality. It is correct. Now, why it is less than b? Actually, this one also we need to identify why it is less than b. Less than b. It is clear. Because b, actually look, b is equal to b over 2 plus b over 2. But if I put less than b, so this is strictly greater than u over 2 plus b over 2, which is u plus b over 2. You see? So b is greater than u plus b over 2. So under this condition, actually u is less than b. Looks like we get the same condition. But here, pay attention. Interesting point. So since this element is less than b, okay, less than b, it belongs to the a. Because b is the upper bound, any element less than here, upper bound in terms of, you know, the for this interval, b is the upper bound, and any element less than this actually is the element of a. Now, if this element of a and u, look, u is strictly less than u plus b over 2, and this one element of a, okay, which contradicts the assumption that u is the upper bound. Now look, this inequality shows we say u is the upper bound, but now we find out that u is element less than the element of a. So it means u upper bound means it should satisfy any element for x from a. It should satisfy greater. But we got the u is the element of a. If you see, if u is less than b and u is upper bound, then we come to the contradiction. So it means the u cannot be upper bound less than the b. So b is a b is a upper bound and the least upper bound. Okay, I think very clear. So you see, we came to contradiction and assumption that u is the upper bound of a. Hence, u greater or equal to b, and b is a supremum of a. So if b is the upper bound, it should be greater than b, no, not less than b. You see, we are coming to the nice conclusion. So if u is the upper bound, then it should be greater than or equal to b. Cannot be less. So this is a very nice proof. Please, similar the argument, you please use it and prove it. Why a is a lower bound of a. Okay, but when you prove it, you have to think very properly. Otherwise, you can come to the wrong conclusion. So here the assumption, your assumption is very important, you know. So for example, U is a lower bound, not least lower bound, just lower bound. Then what kind of assumption you should be? And it is because A is a lower bound, means here A is a lower bound, so means it satisfies this inequality. Then another assumption such that it is also lower bound. This is upper bound. It is a lower bound, but satisfying one type of inequality. At the end, you come up with a contradiction. Okay, so that one you have to put it. Okay, you have to put it. Okay, I think this is the nice proof and a very proper proof. I hope you understand the proof very well. I hope everything is very proper here. Now, there is a very interesting relationship of infimum of A and supremum of A. You see? But please pay attention. Here we are defining minus A is a set of all x, minus x actually, all set of minus x, such that x belong to A. You see? X belong to A, minus x belong to minus A. Okay? So we have such kind of set. So if we define set in this way, then infimum of A is actually minus. You see, we multiply by minus supremum of minus A. So if we find the supremum of minus A, and put the minus, it becomes infimum of A. And proof is also very, very nice. Look, proof. So from the example 2.2, actually example 2.2, it is like this, exactly like this. If x is greater than c, then minus x, when we multiply by x, minus c. So that is we have proved it before. Understand? So just if x greater or equal to c, it is equivalent, the both sides, the if and only if minus x is less than minus c. Now please pay attention. Pay attention. And this implies A is bounded below by C. This one shows A set A. This is actually set A is actually like this. A is the set of x so I can say that all the set x here of course here I can say all the set of x minus x belong to minus A, the sets. Maybe I can define like this because, you know, here it is defined, minus A is defined like this, so A will be defined like this. All the x, all the x belong to the minus A, x belong to the minus A. So here, if x, then you see, if minus x, that one will be minus. So here minus x belong to the A. Here x minus x belong to the A. Yes, yeah, minus x belong to the A. Minus x belong to the A. Minus x belong to the minus A. Okay. So please pay attention. Here, this one shows, because this inequality holds for every x belong to the A. X actually belong to the A. If it is satisfied this, A is bounded below by C. If and only if, but you see, if and only if minus A is bounded above by minus C. So this inequality shows A is bounded below by C, and minus A is bounded above by minus C. So now if A is the infimum of A, so if we are saying if, then minus A is the upper bound of minus A. Because of this inequality, we can make conclusion that if A is the infimum of A, then minus A is the upper bound of A. Because of this inequality, minus A is the upper bound of minus A. If U is another, now here, another assumption, if U is another upper bound of minus A, then minus U is the lower bound of A. So you see, this is A and this is a U. By definition, infimum of A, by the definition of infimum of A, minus U should be less than or equal to A, or hence U is greater than minus A. We have therefore proved that minus A equal to supremum of minus A. Okay, please pay attention. Here, what they are saying. So A is the infimum of A. According to this inequality, this definition, the minus A is the upper bound of minus A. It is correct. If U is another upper bound minus A, means U satisfies like this. Another upper bound if U is another upper of minus A. So means minus X is less than minus if U is another upper bound of minus A. So without just yeah, just like this. For any X from minus A, belong to the minus A. So this is U is another upper bound. Okay. Then minus U. Definitely the minus U will be lower bound of A. So means, so it is less than X. This is the lower bound definition for any X from A. This is minus A. This is A. So minus, if U is the upper bound of minus A, minus U will be lower bound of A. Okay. Now, how we get this minus U? Actually minus U is the lower bound of X, lower bound of A. If A is the infimum of A, minus U should be less. Then this is correct. The minus U should be less than of A, because A is the infimum of A. This inequality must satisfy. Hence, U is greater than minus A. U is greater or minus A. You see, U is greater or equal to minus A. Correct. From here, we can get this. So then, you see, minus A is a supremum of minus A, because this inequality holds for any U belong to the for any U belong to minus A. You see, so little difficulties we have, but generally the steps is correct. You see, if it satisfies like this, then minus A, because minus A is a, minus A is less than for any U. U is a minus U is a lower bound of A. So minus A is a supremum of minus A, or infimum of A is A, equal to minus A is a here when we multiply by you see, A was infimum of A, and minus A becomes supremum of minus A. So if we multiply by A, then we will get minus supremum of A. So that's why this inequality, you see, shows the proof of this. Very nice proof, you see. A is the infimum, minus A becomes supremum of minus A. Then by multiplying minus, we will get equality. So infimum of A is equal to minus supremum of minus A. Okay? So now next is known as a completeness axiom. Now we are coming to the main important theorem, completeness axiom. If A is a non-empty subset of R, which is bounded above, then it has least upper bound in R. Please pay attention here. So, if A is a non-empty subset, it is subset of R and non-empty. So which is not equal to non-empty subset of R, which is bounded above, means that it satisfies this equation. For example, the x less than u for any x from A, So this is means u is the upper bound, which is bounded above. Then it has least upper bound in R. So it means, you see, if it is bounded above, then it has a least upper bound. So I can say B is a supremum of A. Let's say supremum of A, and this supremum is also belong to the R. Actually, this is a completeness means every point every point of R belong to the R. If you see, this one shows there is no gap. For example, this is the we call it R. We call it R. This completeness axiom shows that whenever I take any element on this R, it belongs to the R. There is no gap. If set is bounded, then it has least upper bound. But here, that least upper bound belong to the R. So that's the meaning of the completeness. For example, if I take the rational number set, so Q, if I take the Q, so for example, I am taking any X in R. Then let's say it is bounded by from 0 to B. You see, X varies from 0 to B. So then, of course, B, I can say that it is a supremum. B is a supremum. But B may not belong to the Q. So this set, the bounded set, has least upper bound or greatest lower bound, but that greatest upper bound may not belong to the Q. Okay, may not belong to the Q. So means the completeness, another word of the completeness. So this if set together with together the limit points belong to the set, that set is called complete set. Okay, complete set, which means no gap. Okay, so that's it. So, but from this definition, it looks like if A is a non-empty subset of R, which is bounded above, then it has least upper bound in R. Here, important point is here, upper bound in R. So we cannot go beyond the R. So every element of R is a density and there is no gap. Okay, That is the definition of this axiom. That's why it is a completeness axiom. So R is a complete set. You will see later on that the other set than this rational number set, for example, irrational number set is not complete. It's not complete. Okay. So please pay attention that the completeness means if any set is bounded, then it has non-empty set is bounded, which is bounded above, then it has least upper bound in R. But of the other, for the other set, it might have the least upper bound, but not in R. So that's the big differences between this. Okay, now next important axiom. But this one, you know, we can consider as an axiom. You see, A is a non-empty subset of R, which is bounded above. Then it has least upper bound in R. The second axiom is if A is a non-empty subset of R, which is bounded below, then it has greatest lower bound in R. You see, this is least upper bound. This is greatest lower bound in R. So these two axioms, you know, we just accept, and we can say that the real number set is complete, which means that every element belongs to the R. It cannot be beyond that. So here you can see that the next theorem demonstrates how the set of real numbers equipped with the axiom 4.1, the upper bound, is now large in we have shown. We have shown. We have proved it. Now we can solve this equation and find the solution, and that solution is belong to the R. Okay, you see. Now we extend the equations solution set of the equations. So this equation has a solution, and we know how to solve it. How to solve it? This equation from the calculus. If x square equal to 2, then x equal to plus minus square root of 2, and both of them is belong to the R. Plus square root of 2 minus square root of 2 is belong to the R. Okay, in the R there is a solution. But if I say this plus 2 equal to 0, quadratic equation again, but this equation has no solution in R, has no solution. So we need to extend. That's why, you know, in mathematics, how we extend the set of numbers. If you remember, at the beginning, we start from natural number, starting from 1, 2, and so on. You see, we start from this set, and there are many gaps, very big gaps between them. Then we extend this one, including 0, minus 1, minus 2, and so on. This is also, we call it integer number set. And this integer number set has extension better than this, but this set also not complete, because there are many gaps. So then when we introduce Q, rational number set, which is represented by P over Q, this number is very dense. You will see here also we have the proof of the theorem. P over Q actually is very dense in real number set. Almost there is no gap. Actually, at the beginning of the extension, the scientists said now rational number set is complete. But when they come to the problem of the simple equation which has solution is not in R, in Q has no solution in Q. So they say, oh, here there are many gaps. They found many equations. I can say x square equal to 3. Also, there is no solution in R. But if I put instead of this one 4, yes, it has solution, plus minus 2, plus 2 integer, minus 2 integer. But definitely it is in Q. This 2 is in Q. And this 2 is in P irrational number set as well. Okay, it is a irrational number, it is a rational number, it is an integer number. So this equation has solution in many sets. Definitely it has the 4 is belong to the R. So you see, by coming problem, the scientists start thinking about the extension of the set. So that set becomes, you know, the complex. When they introduce complex number set, then say, okay, we have found all the solutions of the polynomial equations. There is no gap in the complex number set. Then actually later on they introduce another type of sets, which is I cannot say it is a wider than the complex set, but there is a similarity of the set. That numbers I cannot remember. They introduced the new number. Okay, so and for that type of number, many problems can be solved actually. So anyway, so please you pay attention. The rational real number set is complete. Okay, it has if it has upper bound, then least upper bound, and least upper bound belong to the set. Okay, so now we go to the next. Now next theorem. Look, if n is a natural number set and a is greater 0, then there is a number x such that x to the power n equal to a. So this is the exactly I said just now. You see? So now x to the power n in general, not only x squared. So the x to the power n equal to a has a solution. Depending on n. So actually n is root of a. But if I say like this, maybe it is not proper solution. I can say, okay, I can say, so it has solution of this form. It has of plus minus square n is root of a if n is even, and it has n is root of a if n is odd. If n is odd, then it has unique solution. If n is even numbers, then it has two solutions. So, and all of them, this solution belong to the R. You see, there is a number x in R such that this equation has a solution. Okay, and here there is the proof of this theorem. This theorem shows the existence of the positive nth root of a. Okay, nth root or this one for any a, but here a should be positive. Here there is a condition. You see, for this equation, it should have this condition. For this, for even the odd numbers, there is no condition for any a. Because here that it is said a greater than 0, then there is a number x such that x to the power n equal to a. So you can see actually the solution is more wider than this. But for a greater than 0, definitely we have 1. We have You see, for greater than n, this is the solution form. So for taking for n equal to a equal to square 2, we see that square root of 2 belong to the R. And we already know that square root of t is not belong to Q. We must conclude Q is a subset of R, and and the number, this number is called irrational. Okay. Now look, we shall soon discover that the set of irrational numbers, the set from R, if we subtract the all Q, we will get irrational number, is much larger than the collection of roots of natural numbers. Actually, interesting point, that even if the this Q is very dense, but there is a lot of gaps, and collection of that gaps when we subtract this Q. So this one is actually a rational number. I can denote by P. So this irrational number is more than the rational numbers. If more than the rational numbers means actually here for every interval, small interval, a, for example, a plus epsilon, very small interval, there is there is a rational number and there is a irrational number, and irrational number is more than the rational number. So means, you see, the gap in the rational number set actually is a lot, So now next, Archimedean theorem says the set of natural numbers is not bounded. Natural numbers is not bounded above. Okay, this is Archimedes theorems, because from the definition of natural number, we can easily say this is the natural number, actually consists of 1, 2, 3, and so on, infinitely many. Definitely it is unbounded. Natural number set is not bounded, but proof you can see, not very simple, actually, not very simple. From the definition we can say, but here important point, that natural number set is not bounded, okay, and is not complete as well. Okay, is not complete. Okay, I hope this one you can easily understand the proof. For any x, this one is very these two problems are important in many other proof. You see, these two inequality actually important inequality. Please pay attention. For every x positive, for every positive x, there is a natural number n such that x greater than 1 over n. So this definition says, you see, 1 over n. Here we have 0, and 1 over n. Actually, when n getting larger and larger, okay, getting is larger and larger, so it approaches to 0. If n gets larger and larger, getting 0. So for every x positive, there is a natural number n such that x is greater than 1 over n. So it means x, you know, in other words, what we call it. So when n is large number, it is getting closer 0. But there is for n x greater than 1 over n, so means that x is located on the right side of these numbers, So just please take into account. So these two corollaries, you know, says for any positive numbers there is n such that x, whatever large number, whatever small numbers, but for example, for the small numbers, you know, here when n equal to 1, actually this interval becomes 0, x, and 1. Then 1, x less than 2, and so on. Okay. So there is here important one, how there is an n, there is an n, exists n, such that the x lies between n minus 1 and n. So these two inequalities actually very important to prove the other theorems. Okay. For this one, theorem 1 over x is not upper bound. You see, 1 over x, theorem 4.3, there is theorem 4.3, 1 over x, if we opposite 1 over x is not upper bound of n. N. So there is a number n such that n is greater than 1 over x, which implies x greater than 1 over n. From here we can get this equation. Yeah, correct. But actually the n is always greater than 1 over x. So this type of inequality is really important to use to prove such kind of the important theorems. Please pay attention. I think the proof can be understood easily using the above theorem, theorem 3.2, ordering property 3.2. It has smallest element, call it n. Then we can have x less than n, but x not equal, not less than n minus 1. So how to prove? Actually, you see that based on the theorem 4.3. Now I want to prove this one, okay? Because if x and y are the real numbers, x less than y, then there is a rational number r such that x or r belong to between them. So this one shows that rational number is density. Whenever, whatever we get, we take the the real numbers satisfying this equation. Between them there is r. Between them there is r. X less than r less than y. So there is r between two real numbers. So this one shows rational number is a dense. Okay. So that's why how we prove this is a nice proof. We first consider the case x greater than 0, okay? Positive case. If positive, y definitely positive. And since y minus, you see, x we assume like this, and x less than y like this. So from here we can say that y minus x or x minus y, better say y minus x. Y minus x is less, y minus x is greater than 0. From this equation we can get, here we have x greater than 0. So if y minus x, you see, according to the above theorem, this is positive. For any positive number, there is a n. There is n such that y minus x is greater than 1 over n. Okay, because this is a positive number. For positive number, there is a n such that the x, this one, x greater than 1 over n. 1 over n. So 1 over n, correct. Or if I give the common denominator, nx, look, ny minus nx is greater than 1. Okay. Or nx, if I shift to the right, so nx plus 1 is less than ny. We can get this. So since nx is non-negative, we can find another m such that the corollary 2. So this, for the nx, please pay attention here. N times x. If y it is positive, n is a positive, x is positive, so n times x is positive. And for any positive numbers, corollary 4.2 says there is a M in the natural number set such that this inequality holds. So from 1 and 2 implies how we get this inequality. Actually, it is not big problem. You see, look, we have this inequality. We have this inequality. So then we have this inequality for nx. Nx less than m greater than m minus 1. M minus 1. Now, if I put here for the nx, nx less than m, nx less than m, this one given according to this, and it is less than m. Of course, and if I add nx 1, definitely the m will be less than this. So now why nx plus 1 is less than ny? You see, nx m and less than ny. When we divide by n, you see here we have x is less than m over n, and less than y. You see that the last one is ny. So from this and from that, we can get this. This one is a rational number. This is the r. So r belong to the x and y. So that's very nice proof that rational number has satisfying this inequality, which means it is a dense. For any closed xy, we can find r satisfying this inequality. Okay, so now another point: if x and y are the real numbers satisfying this, then there is a irrational number t such that, you see, for the irrational number also we can prove. This shows that irrational number is also dense in R, is dense. But in both cases, in R, in irrational number, there is a lot of gap, okay? So here, this is the second proof. And the last one, just a subset C of R is complete if every non-empty bounded set of C has both supremum and infimum in C. Okay. Now this one is another completeness of the set. So subset C of R is complete if every non-empty bounded, you see, non-empty bounded subset of S, subset of C has both supremum and infimum in C. Here, important one, you know. So every time we can get supremum and infimum. But if this supremum and infimum belong to the same set, that one is complete set. Okay. The rational numbers are not complete. This one I leave it for you. Rational numbers are not complete. Very nice proof, and Q is not complete. Okay, so please read this one. I'm going to give just 5 minutes rest, stop sharing, and we go to the next topic. Okay, are you hearing me well?
Yes, doctor.
Okay, so please now relax another 2-3 minutes. Then we continue the second chapter. Actually, very much we are behind, but at least we learn many good things, right? So practicing many examples, and please be ready for exam tomorrow. Okay, just relax. Today very strange. No, my video, but Alhamdulillah, you are. My microphone is okay. You can hear me well. Okay, just relax. Please, who didn't sign, please sign. Okay, register, please. Okay. Now let me start the second chapter. Yeah, time is running very fast. Okay. So let me sharing again. Okay, sets and functions. Now, in this chapter, actually, we learn what is the sets and what is the functions, what kind of relationships, and how to differentiate it. Okay. So the first one, functions. Let A and B be element in any set. By definition of equality between sets, we have AB means it is AB or BA. As a set, you see, if we repeat A many times, we can consider as a one element. So this set actually equal to this set and this set equal to BA. If we change the order, still it is the same. This means that repetition of element in a set doesn't change the set, and that is the order of the elements in the set is irrelevant. So the ordering is actually irrelevant because AB and BA are the same set. So this one is irrelevant. Ordering of elements. If we wish to give significance to the order, we shall write. You see, now please pay attention. This one also set. This one also set, but this one is an interval set. This is a what we call it discrete set. Discrete set. But in the interval set, AB is not equal to BA. Okay, the ordered pair AB. So thus, if AB equal to C, implies A equal to C, B equal to D. Hence, AB equal to BA, if and only if A equal to B. Another word, so in the interval set, equal to BA, if and only if A equal to B, which means only one element. Only one element. A is called the first coordinate and B is called the second coordinate. Okay, so this is the just general statement. Now the definition. Let F and B be sets. The Cartesian product of A and B, denoted by A times B, is the set of all ordered pairs. You see, all ordered pairs, such that A belong to A, B belong to B. You see, one element from A, one element from the B. Symbolically, we have, this is a Cartesian product of two sets. It is the AB, the element of in R square, such that A belong to the A, B belong to the B. For example, if A Cartesian product B is empty set, if either A empty set or B is empty set. You see, if one of them is empty set, second one is not empty set, but product still call it the empty set. For example, 1, 2, and 3, 4, 5. So Cartesian product of this actually has how many elements? 1, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5. Note that opposite 3, 4, 5 and 1, 2. 3, 1, 3, 2, 4, 1, and etc. 5, 5, 2. Look, they are not equal to 1, 2, and times the product, Descartes product or Cartesian product of, you see, they are not equal actually in terms of the definition. Because, you know, 3, 1, for example, is not equal to 1, 3. Actually, in terms of a number of elements is the same. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Both of them 6 elements. But 1 3 is in the Descartes coordinate system is element which is not equal to 3 1. So you see this product, Cartesian product, is not equal to that product. Okay, in general, B is a Cartesian product B is not equal to B Cartesian product A. Okay, next, for any sets A and B, a subset of A times B, Cartesian product of AB, is called a binary relation from A to B. You see, is called a binary relation from A to B. A subset of A times A is called a binary relation on A. You see, AA also can, BB also can, but if a subset of AA is called a binary relation on A. Example, if R is a relation from A to B, then R is a subset of Cartesian product of AB subset. We generally refer the binary relations as a simpler relations when there is no need to emphasize its binary nature. Okay, if R is a R means is not what you call it, is not real number set. This R is a relation from A to B. For example, R1 is 1 3 1 4 and 2 5. Just taking of from the Cartesian product of these two numbers. So R1 is like this, R2 is like this, R3 is like this, R4 is like this, R5. You see, we can generate the subset of Cartesian product from given sets. This is all subsets of Cartesian product. Okay. Now, what we can say about this? If when AB is a subset, is an element of R, we say that A is related to or associated with B by R. We sometimes express this symbolically by writing ARB. One of the important binary relations on R on N is a relation greater than, which is expressed by. Okay, now look, 2 1 2 1 3 1, not creating from this actually this one one of the important binary relations on R is a relation greater than, which is expressed by this. So this is also expressed by writing 2 greater than 1, 3 greater than 1, and so on. 4 greater than 3, 5 greater than 1. Actually, this is ordering, where is a conventional mathematical symbol for greater than. Okay. Generally, for example, here, of course, the second element always less than the first element. We have the some order, but it might not be this the ordering like that. One is greater, second one is less. Can also happen. If R is a relationship from R from A to B, then inverse relation R minus 1 is a relation defined by BA, where AB from R. Okay, please pay attention here. What they are going to say actually. Okay, still cannot. So what they are going to say. Okay, now we have set A. I can say okay, actually our set is like this. Our set is AB. Here A element from A, B is element of B, and this one is relation. This one is a relation. So now the definition 3 says, so if R is a relation from R from A to B, the inverse is a relation defined by BA. Okay, look, I will take just R1. R1 actually is like this. R1 has this element 1 3 1 4 and 2 5. Okay, what about R minus 1, the inverse of this set, this binary set. So actually it is 3 1 4 1 and 5 2. So the inverse, look, 3 1 4 1 5 2, because definition says that the inverse relation is a relation defined by the AB from R. You see AB from R. So R minus 1 actually is a consists of the element BA such that AB from R. So this is the definition. R was the set of A, B such that A belong to the A, B belong to the B. Okay, so R relation has this type of set. So R minus 1 becomes BA, where AB is from R. AB from R. Okay, so by using this definition, you can easily find the inverse relation. I think this one no problem. You can make it. A relation R from A to B is called a function. Now you see, slowly we are coming to the function. Relation R from A to B is called a function or mapping from A to B. If for every x there is an element of B such that x, y belong to the R. Second, whenever x, y from R and x, z from R, then y equal to z. Y equal to z. Look, so the second relation, second relation says if we consider x, y, the element of R, and second x is the same, but z also R. In that case, so y be equal to z. So actually, you see, if x, y, and x, z belong to the same R, then y should be equal to z. Should be equal to z. So this is another definition. Relation R from A to B is called a function. Okay, and is called a function if two conditions hold. For every x, there is a y such that x, y belong to the R. And whenever x, y belong to the R and z, x, z belong to the R, then y equal to x, y equal to z. In other words, a function from A to B is a relation in which every element of A is associated with one element in B. For example, among the relations in 1 to 5, we see that R2 and R3 are the functions from 1 to 3, 4, 5. In R and R4, the element 1 belong to the 1, 1, 2 is associated with more than one element in 3, 4, 5. What does it mean? So actually now the here definition says the relation R from A to B is called function or mapping. Usually, in calculus, we easily and very clearly say the function in the form of this. This is the we call it function. Now, if I just extend this in the form of like this. Okay, so this function I am writing in the form of R, such that y equal to fx. You see, so usually, actually, this function has a relation in R, has a relation in R with this. So every here x, actually x, we know the domain of f, domain of f. So x, when x varies on in the domain of f, y takes value according to the values of x. So if we collect all such pointers, we will get a relation between x and y. Okay, now but in here, if xy belong R and xz belong to R, then y equal to z. So this condition actually gives another type of relation, another type of relation. You know, in the usual case, if xy, look, xy belong to the R square and xz belong to the R square. But from here, we usually don't say y should be equal to z. It is not necessary in usual the R square definition. But here you see definition is given in the form of relation R. For the relation R, so this case actually is different. Please pay attention. According to the definition, we handle the problems. Okay. Now, in other words, the function from A to B is a relation in which every element of A is associated with the with one and only one element in B. So actually, you see the A from capital A, which is actually domain in terms of function. Actually, A is a domain. B is a range. And this relation in the function cases, as I told you, that it has relation between x and y. But here, just as a point, we consider as a point. You know, xy is a point in R. R is a relation. Okay, R is a relation from A to B. So okay, you see, currently here, among the relation 1 to 5, this 1 2 3 4 5. Okay, let me show one of them. So we see that R2 and R3 are the functions from 1 to 2 3 4 5. Okay, what about R2? R2, okay, if I R2 is a set of this one 1 3 and 2 4. It is this is the R2 and R3. R3, what they are going to say? R3 is 1 5 1 5 R3 and 2 5. Okay, so here it is said, we see that R2 and R3 are the functions from 1 to 2 3 4 5. 1. So from here, what about, actually look, in both cases, A consists of two elements, right? So the 1 and 2. 1 and 2. 1 and 2. A from here, then the first element, 1 2. 1 2. B has 3 4 5. 3 4, 5. It is correct. It is correct. You see, the R2 function from 1 to 2, 3, 4, 5. R1 and R4, the element 1 belong to the R1, 2 is associated with the more than one element. 3, 4, 5. You can check. Huh? So generally, the statement xy from f, f is a function from a to b. The statement x, you see, actually, in real analysis, the simple problem we are expressing in the more complicated form. You see, now they are formulating the function. The statement xy belong to the f is expressed as f mapping x to the y, or like this. This is very familiar. We are very familiar. Actually, this function, they are making the complicated forming the definition of the function. Why? Because in the real analysis we need some extra point which cannot be expressed in the calculus. So that's why they are trying to bring up what is the relation first. Then this relation brings to what type of problems. What is the connection between two sets? You see, from here, for example, I can see 1, 2, 1, 2 from A doesn't change, but for the B has more element than 3. So generally, the definition 1.4, see 1.4 definition, there is only one image for X, but there may be more than one pre-image of Y. It is correct, for every X, we might have many Y's, many Y's. Can I give an example? Okay, let me first a little bit look at the next. F of x is also referred to as a value of function. Okay, this is just the definition. They said A is a domain of definition. Then denoted by df. The B is codomain. Another name is a codomain, or we call it range. Thus, function f is completely determined by its domain. Its codomain is B, and rule is f of x, which assigns to every element of x a image B, y in B. This is expressed concisely in the form. Okay, this is the form calculus. If C is a subset of A, C is a subset of A, the image of C and the F is a set. But please pay attention. Now, here, this type of notations, bring this different type of problems. F of, you see, capital C. Capital C is actually capital C is a subset of A. Capital C is a subset of A. And how we, how we get the f of C, not f of x. So it is a set of f of x such that x belong to the C. So actually, f of C is what we call it, is a set of all the function's value when x belong to the C. So this one actually in many cases gives some kind of interval, which is subset of B. So this one is a subset of B. Why? The set is like this, composed of the image and the f of all elements of the domain of F. Is called range of F and denoted by RF, range. Okay, generally, why it is said, so the if set is a subset of A, the image of C and the F is a set, and which is a subset of B. They say this is a subset of B. Why? Because look, actually, this is function. X varies from A. Then B is a set of all Y, actually all element of Y, such that this has this relation of element of, you see, the B actually is a set of all element of Y, where Y has a relationship of X, where X belong to the A. So the B is a large set, and if C is a subset of B, definitely F of C is a subset of F of B, because B is a large set. Then the F of C is an interval, some certain type of interval or discrete numbers, but it must be subset of this. This is correct. So now the set composed of the image and the F of all elements of the domain of F is called range. Now this one is called actually range. But please pay attention. This F of C is different. Now F of A, which is defined by F of X, it is a set of all F of X such that X belong to the A. The set composite of the image and the F of the all elements is called the range of F. F of A is actually, this one is called the range. Yes, it's called range, correct. And clearly RF is a subset of B. Clearly RF. But you know, if it is like this, generally RF can be equal to B, because here, you know, this F mapping A to the B, A is the domain of F. So if F is the domain of F, then RF, which is F of A, actually should be equal to B. But why? Clearly they say that it is a subset of B, because here I am taking all the element of the set in A. To me it is the same. Okay, now look how we find it inverse in the form of the functions. Actually inverse in general given like this, but actually it is not easy. Here please pay attention. The previous relationship, look, in the previous relationship, inverse of R1, for example, if I have R1, 1, 3, 1, 2, for example, 2, 4. I have, let us say 3 elements. R1 minus 1 was very easy, just opposite, 3, 1, 2, 1, and 4, 2. You see, this one we call it inverse relations. But in terms of the function, if doesn't guarantee the existence of the pre-image. Actually, definition 1.4, correct, doesn't guarantee the existence of the pre-image X from A such that F of X equal to Y. Now look, usually function we write like this, simply, very easy, and where X belong to the A, which is A is a domain of F. So now if Y belong to the B, definition 1.4 doesn't guarantee the existence of the pre-image X from A. So now imagine in the form of the set. So this is a set of A, and this is the element of the A, and this is the set B, and this is the element of B, and this is the rules. We have F rules. So now, actually the pre-image, this one we call it image. This one we call it image. Image of X. Image of X. So this Y is the image of X. Pre-image, pre-image, -1. So for any given Y, we should find the element in A, such kind of X1, another element. This is X element. So this is the image. This one is pre-image. Pre-image. Pre-image of Y. Pre-image of Y. Okay. So it is said, the definition doesn't guarantee the existence of the pre-image. Okay, it is correct such that f of X equal to Y. In equation 2, for example, the 5 has a no pre-image under R2. So in equation 2, 5 has no pre-image under R2. Okay, let me example 5, for example, in equation 2. Okay, let me just write equation 2, equation R2 is 1 3 and 2 4. Okay, this is the if R is a relation from A to B, we have some examples. Okay, this one. Okay, now what are they going to say here in equation 2? For example, 5 has no pre-image under R2. Why? R2, if R2 has this type of element 1 3 and 2 4, then it is that R2 for example 5 has no pre-image under R2 because 5 is not there. Furthermore, if the pre-image existed, it might not be unique, as may be seen in the equation 3, where both 1 and 2 are pre-image of 5 under R3. Okay, actually, you see, in terms of example they have given, but generally in the calculus also we have seen. So the pre-image may not be exist. You see, image exists, a pre-image may not be exist, or the pre-image might be not only one, many. So that's why actually when we come up with the one-to-one function, okay, they are trying to come up to the one-to-one function. Next, tomorrow I will teach you how to explain this part. Tomorrow we will discuss. Okay, and this is the beginning and equivalent sets. Okay, I hope tomorrow I will continue. Thank you very much, and stop at this point. So tomorrow, are you coming to the class, the auditorium, or all of you joining in internet? How many students staying in campus UMT? If it is required tomorrow, I will go to the auditorium. Today I didn't go.
Doctor, I think better online for now for the first week because we are having connection problem if it's hybrid. Just now also the first class before this class we had some problems.
Actually, tomorrow is the exam, so I think I will. If they don't mind, I will be at home. From home, I have good internet because you know, like today, if we have problem, then exam problems, right?
Yeah, yes, doctor.
Okay, I will ask them to handle the class tomorrow from home. Otherwise, You will have problem, I will have problem here. Okay, see you tomorrow, huh? So please revise chapter 1 and 2 types of lecture notes. Please revise it. And induction. Almost I told you what is their problem, huh? Please revise. And if you have any questions, please contact me. Thank you.
Thank you, doctor.
Thank you, Ata.
Thank you.
Thank you, Doctor.
Thank you.